Let's look at the graph of limaçons. So what I want to start here is comparing what the polar graph would look like versus the sinusoidal graph. So the sinusoidal graphs are what we looked at in our previous units where we talked about graphing sine and cosine functions. So on the left graph, we had the polar grid. So we have the origin, we have these concentric circles. Each circle represents a a increase in radius by 1 unit. And then we have all these sort of slanted lines coming in, and each of those just represent different angles. Okay. And so I want to look at the graph of r equals 2 plus 3 sine of theta. Okay. And so that's the polar graph. And I want to convert that and look at what it looks like as a rectangular graph. So if I replace the r with a y and the x, or the theta with an x, then instead of r equals 2 plus 3 sine theta, I have r equals 2 plus, or sorry, I have y equals 2 plus 3 sine x. So what does the graph, let's start there. What's the graph of y equals 2 plus 3 sine x look like? Well, remember the 2, that's our vertical shift. And so that means the graph has been moved up 2 units. That's also the midline of the graph, so kind of that horizontal middle of the graph. The 3 is the amplitude, so it tells me from the middle of the graph how high up it goes and how far down it goes. So from 2, it's going to go up 3 units to 5, and it's also going to go down 3 units to a -1. Right? And then just in general, the sine graph, it has a period length, standard period of 2 pi, so from 0 to 2 pi, and we're not messing with that right here. It starts at the midline, it goes up to the max, back down to the midline, down to the minimum, and then back up to the midline. Okay, so it's got kind of that wave kind of shape just for one period. Okay, so what I want us to see here is as we track points along that sine wave graph, how does that correspond to the graph of the limaçon that we're going to see in our polar graph? Okay, so remember that the x value for our sinusoidal graph corresponds to theta on our polar graph. So on the sinusoidal graph, as we move from left to right, from 0 to pi over 2, that's going to correspond to a rotation in a counterclockwise direction from 0 to pi over 2. So that means we're going to see our graph rotate once around the unit circle from 0 to 2 pi. Okay. Now it's not going to create a circle of a graph, but we're just going to rotate once around the circle. The other part that we want to look at is, so as we rotate around 0 to 2 pi on our polar graph, which is going left to right from 0 to 2 pi on our sinusoidal graph, what does the y value represent? So on the sinusoidal graph, the y value is just the height above the x-axis. So we can kind of see right now the x value is 0, the y value is 2. So it's 2 units above the x-axis. How does that correspond with the polar graph? Remember, the y value is the r value. So if the y value is 2, which is where we're starting, then that means the radius value is also 2. Okay, so the very first point on our graph has an x value of 0 and a y value of 2. And so that means the very first point on our polar graph has an angle of 0, which means it's on the positive x-axis, and a radius of 2. So it's going to be on the x-axis 2 units away from the origin. Okay. Now, as we take our sinusoidal graph, y equals 2 plus 3 sine x, as I start to move from left to right, as I start at x equals 0 and travel to the right until, let's go until we get to x equals pi over 2. So as we go from 0 to pi over 2, that's going to correspond on the polar graph of rotating from 0 to a pi over 2 angle. So that's going all the way through the first quadrant of the graph, so 90 degrees. We're going to rotate through that 90 degrees. As we do that rotation, the y values go from 2 up to 5, which means the radius values also are going to go from 2 to 5. So as I rotate through this first quadrant, I should see the radiuses increase from a 2, so I'm still just rotating in a counterclockwise direction, we see the radius change from a 2 up to a 5. And that happens as we just rotate our angle through the first quadrant, so from 0 to pi over 2. Right? As we continue moving from left to right, so from pi over 2 to pi. So right now at pi over 2, the y value is 5. Once we get to pi, the y value goes back to 2. So it's going to change from 5 and it's going to decrease back to 2. Well, going from pi over 2 to pi on our circle means we're going from the positive y-axis over to the counterclockwise to the negative x-axis. So we're going to rotate again 90 degrees from pi over 2 to pi. As I do that, the radius is going to have to change from a 5, and it's going to decrease back to a 2. So we're going to see kind of a similar shape that we saw in the first half. So as we rotate through that second quadrant, we're going to see the radius value change from a 5 and decrease and get smaller back to a 2. Okay, so that's the first half of the graph. That's nice and easy. Okay, things are going to get a little more interesting from here. As we continue moving left to right for our graph, so going from pi to 3 pi over 2, on the sinusoidal graph, notice that it's going to cross the x-axis. As it crosses the x-axis, that means the y value is going to be 0. Well, what does it mean for a point to have a radius of 0? That means the point, if you have a coordinate that has a radius of 0, that means it's actually at the origin, at the pole of our polar graph. Okay, so as we start rotating into the third quadrant of our polar graph, we're going to see the radius get smaller and smaller and smaller until our point, which means our point is going to get closer and closer to the origin. And again, that's going to happen as we continue rotating counterclockwise. And eventually it will hit the origin around 5 pi over 4. So let's kind of see how that happens. So as we're rotating down, that radius is getting shorter and shorter and shorter until eventually we're going to see it actually connect to the origin. Okay, and that's, again, where our sinusoidal graph is at the x-axis. Now, between around a 5 pi over 4 to around a 7 pi over 4, so if you look at our sinusoidal graph, as we pass through that 3 pi over 2, all of those y values are negative, right? The graph dips below the x-axis on our sinusoidal graph, okay? Well, what does it mean if y is negative, that means the point is below the x-axis. What does it mean for a radius, for r to be negative? Remember, we've seen that if r is negative, we have to take that coordinate and flip it in the opposite direction. So kind of a complete 180 degree flip. Okay. So that means if my angle is pointing into the third quadrant and I have a negative radius, the point is going to flip diagonally into the first quadrant. If I have a point in the fourth quadrant and a negative radius, it's going to flip the point and it's actually going to end up in the second quadrant. If I have a point on the negative y-axis with a negative radius, it's going to flip that point up to the positive y-axis. And so that's what's going to happen as we continue rotating. Notice my angle is pointing into the third quadrant right now. Okay, we're approaching 3 pi over 2. We're getting closer to the negative y-axis with my angle, but the point is up in the first quadrant because it has a negative radius. And once I actually get to the 3 pi over 2 angle, the radius there has a -1 value because the y value is a -1. And that means the point is actually flipped in the opposite direction. So instead of the point on my polar graph being at the 3 pi over 2 angle, it actually looks like it's up at the pi over 2 angle, okay? Because it's flipped up across the origin. And that's going to happen again as we continue rotating into the fourth quadrant, but now the values are getting closer to 0, so the radius, the point is going to get closer to the origin. Still negative though, so it's flipped in the opposite direction until we get back to 0. And then once we pass 0, the sinusoidal function becomes positive again. It's above the y-axis. And so now the point is going to be in the same direction as my angle. And as we follow our sine graph, we're going to see the y value approach 2 again as we get close, as x goes to 2 pi. And so it's going to go back to where we started on the polar graph. So this is just kind of hoping to help you see, if you took the graphs that we've already studied, the sinusoidal graphs, y equals x sine x, y equals cosine x, we can take those and basically map them into this polar form. Okay, it's just instead of x's and y's, it's thetas and r's. It's rotations and radiuses. Okay, so let's look at these in a little bit more detail. All right, so here we have, again, a Limaçon graph, and it's the same equation that we had, r equals 2 plus 3 sine of theta. And so if we saw, what we saw before is this graph it's almost a circular graph. It looks kind of like a circle, but at the bottom it's kind of, it curls up more steeply and intersects the origin, and there's the second loop. And so this type of a limaçon, so limaçon is kind of the big family name. Within the limaçons, there are several subgroups that we're going to have, subcategories. And so this particular kind of subcategory we call the inner loop. So there's the big outer loop, and then there's the small inner loop. Okay. And then there's two others that we're going to see as we keep looking at this. So what are those different shapes, and then how do we know when we have them? So right now we have r equals 2 plus 3 sine theta. What would happen if I changed the 3 to a 4? So if I have r equals 2 plus 4 sine theta, notice the graph is the same. Okay, it's gotten a little bigger, but the inner loop is still there. The inner loop's a little bigger. And if I had r equals 2 plus 5 sine of theta, same thing. It's another inner loop. Everything's just a little bigger. Okay. What happens if I make it r equals 2 plus 2 sine theta? So with r equals 2 plus 2 sine theta, notice that the inner loop just disappeared. The overall graph is actually still, the outer loop is still there. The overall outer loop is still there. We've just lost that inner loop. Okay. And so this particular graph here, you might think it kind of looks like a heart. And so we call this a cardioid. So we get, again, that cardioid root word comes from your heart, from heart. So we have a cardioid. What's the difference in our equation between cardioid and an inner loop? The inner loop happens if the B value is bigger, so A value is smaller. The cardioid happens if they're equal to each other, if the 2 and the 2 are the same. Okay. So then what happens if the B value gets smaller, if the A is bigger? And so if we had, say, equals r equals 2 plus 1 sine of theta, or r equals 2 plus sine theta, it's now almost a circle, but the bottom of the graph is just kind of flat. Okay. And so we'll see this exaggerated, that flatness exaggerated a little better, but we're going to refer to this as a dimple. Okay. So the three graphs that we have for limaçons are the inner loop, the cardioid, and the dimple. Okay. We get the inner loop if the A value is bigger, if the A value is smaller. We get a cardioid if the A and the B are equal to each other, and we get the dimple if the A value is bigger. Okay, so again, inner loop, A value is smaller, cardioid, they're equal, dimple, A is bigger. Okay, so just to see kind of what these look like, again, let's look at a slightly different function. Let's make the A value a 4. And let's make the B value also 4. So if we have r equals 4 plus 4 sine of theta, because the 4 and the 4 are equal to each other, the A and the B value are equal to each other, that's cardioid. Okay. If we had r equals 4 plus 5 sine theta, again, 4 is smaller than 5, so we have the inner loop. And if we had 4 plus 3 sine of theta, notice, again, it looks kind of like a circle, but the bottom edge of that circle has been kind of pushed up and inward a little bit. And so that's where we get to see that dimple a little bit more. But basically, the dimple is like it's trying to be the cardioid. It's trying to go up to the origin, but it doesn't quite reach up to the origin. And so it's got that, it's sort of trying to reach up to the origin, but just not quite make it. Okay, so that's what that dimple looks like. As the values get further and further apart, so if we have r equals 4 plus 2 sine theta, we see less of a dimple and more of it kind of flattens out. And as they get further away, again, we're going to see it looking more and more like a circle. In fact, if the b value is 0, so if you have r equals 4 plus 0 sine of theta, that's actually just r equals 4, right? The 0 sine of theta just goes away. It's a 0. And r equals 4 is a circle of radius 4. So as we start adding in the sine value, as it has a larger and larger coefficient, we see that graph shifting upwards. We see that dimple effect coming in the bottom, and then we see it turn into a cardioid, and then we see it turn into an inner loop. Okay, so that coefficient, that 5, in this case, r equals 4 plus 5 sine theta, that 5 is affecting how much the graph is getting pushed upwards, but it's almost getting pushed upwards from underneath. Okay. So some other things to look at. What would happen if we looked at this as a cosine graph? Okay, so if we did cosine, the graph switches direction. So if it's sine, the graph is sort of symmetric and oriented on the y-axis. If we do cosine, it's oriented on the x-axis. Okay. And then what would happen if we made it, instead of a 4, say a 4 plus 5, what if we did a 4 minus 5? So if we have r equals 4 minus 5 sine theta, notice the graph actually goes down now. And same thing if we did switch this to cosine. It's now going to the left. So r equals 4 minus 5 cosine of theta goes to the left. So if it's a sine equation, the graph is oriented and symmetric on the y-axis. If it's a plus, it's going up. If it's a minus, it's going down. And if it's a cosine graph, it's symmetric and oriented along the x-axis. If it's a plus, it's to the right. If it's a minus, it's to the left. Okay. All right. Just a few other things we want to look at is, where does the graph touch the axes? Where does it intersect our x and y axes? So if we have, say we have the equation r equals 3 plus 3 sine theta, the graph will hit the horizontal, the perpendicular axis. So since it's sine, it's oriented vertically on the y-axis. It is going to hit the x-axis at 3. Okay. Where does it hit the y-axis? It hits the y-axis at 6. Okay. So it's going to hit the y-axis at the sum of the 3. So 3 plus 3 is 6. Okay. What if we changed our equation a little bit? Let's do an inner loop. So let's say we have the graph of r equals 3 plus 4 sine of theta. Because it's sine and it's a plus, it's oriented upwards on the y-axis. Where does it hit the x-axis? It hits the x-axis still at 3. So that means the a value is going to determine where it hits that perpendicular axis. So since it's oriented on the y-axis, the perpendicular axis would be the x-axis. And it hits the x-axis at 3 and negative 3, or it hits the x-axis on the circle of radius 3. Okay, where does it hit the y-axis? So our axis of symmetry. Well, at the very, very top of the graph, it hits at 7, and then the top of the inner loop is at a 1. Well, where do we get a 7 and a 1 from? Well, if we take the a and the b values, the 3 and the 4, what's 4 plus 3? 7. Right? What's 4 minus 3? It would be a 1. So is that going to be true if we change our equation a little bit? So what if we have r equals 3 plus 5 sine theta? Okay, it still hits the x-axis at 3 on the circle of radius 3. Where does it hit the y-axis? Well, this time it's hitting the y-axis at 8, and the inner loop hits it at 2. Well, 5 plus 3 is 8, and that's where it hits it at the top of the outer loop. 5 minus 3 is 2, and that's where it hits it at the top of the inner loop. So just kind of in general, we could think of, for the inner loop graphs, 5 plus 3 or b plus a, and then 5 minus 3 or b minus a is where it's going to hit the axis of symmetry. And that's going to be true whether we're talking about a sine graph or a cosine graph, right? If we have r equals 3 plus 5 cosine theta, 5 and 3 make an 8 and a 2, And so it's going to hit the x-axis now at an 8 and a 2. And it's true even if we have a negative in there. Think of the negative as just telling you the direction. Okay, if A is 3 and B is 5, well, that's still an 8 and a 2. If we add and subtract them, 8 and a 2. And this time, but this time they're to the left. So they're kind of hitting the negative x-axis at negative 8 and negative 2. Okay. And the same thing would happen if we had a dimple graph. Okay. So let's look at a dimple graph here. So say we have r equals 4 plus 3 sine theta. That's oriented on the y-axis. Now it's going to hit the x-axis at 4 because that's the a value. And if we do b plus a, we get 7. So it's going to hit the y-axis as a positive 7. And if we do b minus a, it's going to be a negative 1. So 3 minus 4 is a negative 1, which notice that's where it hits the y-axis at a negative 1. So it's hitting it on the opposite side of the origin. And that's where we get that little dimple effect. Okay, so it's hitting the y-axis at 7 and at negative 1. And the same thing would happen if we switch this to cosine. R equals 4 plus 3 cosine theta hits the y-axis at plus or minus 4, so the circle of radius 4, and it hits the x-axis at 7 and negative 1. And again, the same thing would happen if we switched it to a minus. So if we had it going to the left, it's going to hit it now at a 7 or negative 7 and a positive 1, so to speak. Okay. All right, so that's what the limaçons look like. Let's kind of summarize that again and then look at some examples. All right, so just a quick summary of limaçons. The equations have the form r equals a plus or minus b sine of theta, or r equals a plus or minus b cosine of theta. We're going to have an inner loop if the a value is smaller than b. We're going to have a cardioid if the a is equal to b. And we're going to have a dimple if a is greater than b. And when you think about comparing a's and b's, just ignore the signs altogether. It's just the absolute value of a and b. In terms of the axis of symmetry, kind of the main orientation of the graph, it will be in the y direction if sine is positive, if you have sine, and it'll be in the x direction along the x-axis if you have cosine. Okay, it will extend upwards and to the right, upwards or to the right, if you have a plus, and it'll extend to the left or down if you have a minus. It'll intersect the axis of symmetry at b plus a and b minus a, and it'll intersect the perpendicular axis at plus or minus a. All right, let's look at a couple examples where we have a graph and we want to write the equation. So this first graph, what we see is we have a cardioid, right? There's no inner loop, and it does actually touch the origin in the middle here. So this graph is a cardioid that extends to the left. It crosses the y-axis at 4 on the unit 4 circle, the circle of radius 4. It does touch the origin, and it extends to the left and crosses the x-axis at the circle of radius 8. Okay, so just kind of piecing that information together. Because it's along the x-axis, I know it's going to involve cosine, and since it's to the left, I know it's going to be minus. So r equals a minus b cosine of theta. Okay, I know I can get the a value because that's where it crosses the perpendicular axis. So cosine means it's on the x-axis, so the y-axis perpendicular to that, it crosses at 4. So I know a has to equal 4. But because it's a cardioid, I know that the a and the b values have to be equal to each other. So if a is 4, b also has to be 4. So my equation for this graph is going to be r equals 4 minus 4 cosine of theta. All right, let's look at a second example. This time we have a graph. It looks like it's a dimple. Okay, it does not have an inner loop, and it does not reach up and touch the origin. So the bottom of the graph is just kind of bumped up a little bit. So that's a dimple. And it is also extending vertically in the positive y direction. Okay, so because it's in the y direction, a positive y direction, I know my graph or my general equation is going to be r equals a plus b sine of theta. Okay, and because it's a dimple, I know that the a value is going to be bigger than the b value. Okay, so we just need to figure out what the value of a and b actually are. Because the axis of symmetry, the direction this graph is oriented is along the y-axis, that means the perpendicular axis is the x-axis. And our graph hits the x-axis at the circle of radius 5. And so that tells me the a value has to be 5. So how do we find b? Well, I know that b plus a has to be a point on the graph. So b plus a is going to be an 8. And I also know that b minus a has to be the other point on the graph. So that's going to be a negative 2. So b plus a has to be a 5, and b minus a has to be a negative 2. And you can use either one of these and just take the a equal to 5 and plug it in for a. So b plus 5 has to equal 8, which means b is equal to 3. And if you did it using the other equation, b minus 5 has to equal a negative 2. But if you add a 5 to both sides, you get, again, b is equal to 3. So either way, it doesn't matter. We get a equals 5. We get b equals 3. So my equation is going to be r equals 3. Sorry, it's going to be 2. R equals 2 plus 3 sine of theta. All right, let's try a couple examples where we're given the equation and we want to sketch a graph. So our first example, we have r equals 3 minus 3 sine of theta. So as soon as we see the sine, we know this is going to be on the y-axis. Because it's a minus, we know this is going to be going down. And because the a value is equal to the b value, because both of them are 3, we know this is going to be a cardioid. Okay. We also know the a value is 3. And so the graph is oriented vertically on the y-axis, going down. And the a value tells me where it's going to hit then the perpendicular axis, which would be the x-axis. So it's going to hit the graph twice on both sides of the x-axis at where the x-axis has a value of 3. It's also going to touch the origin because that's what the cardioids look like. And then the other value point on the cardioid we can get by doing b plus a, which b plus a is going to be 3 plus 3, which is 6. So it's going to be 6 units and it's down. So it's going to go 1, 2, 3, 4, 5, 6. So it's going to be down on the y-axis where the y-axis intersects the circle of radius 6. So this gives us 4 points to draw to sketch our cardioid. And usually I'll just try to start at the origin and kind of loop around through the 2 points on the x-axis, and then kind of just try to draw as circular as you can make it, so kind of as smooth of a curve as you can make it as it goes and extends through all of these points. Okay, that was not maybe the best, but that's kind of what it'll look like. All right, so it starts at the origin and it loops up and around through the x-intercept, down and around through the y-intercept, back up through the x-intercept, back curving around back to the origin. Okay. All right, let's try one more. R equals 2 plus 5 cosine of theta. So again, as soon as we see that cosine, I know this is going to be oriented along the x-axis. It is a plus, so I know that means it's looking, or it's going to be oriented to the right. And my a value is 2, my b value is 5, and since the a value is less than the b, I know this is going to be an inner loop. Okay, it is oriented in the x direction, so that means the y-intercepts are going to be at a. So on the y-axis, we're going to go up 2 units and down 2 units. That's where it's going to hit the y-axis. Inner loops also hit the origin. And then we're also going to hit the x-axis at b plus a, and at b minus a. So b plus a is going to be 5 plus 2, which is 7. And b minus a, that's going to be 5 minus 2, which is 3. So it's going to hit the x-axis at 7 and at 3. All right, so to draw this graph, we're just going to start at the origin and kind of loop down through our y-intercept, and we're going to continue curling out and around through our x-intercept, up and around back to our y-intercept, from our y-intercept to the origin, and then from the origin we'll just create a little loop through the x-intercept at 3. And so that will be roughly what our inner loop graph for r equals 2 plus 5 cosine of theta.